Hey friends, MoNaCo here with our fourth homework video for atomic theory. This video is focusing on isotopes, their notations, and their definition, what an isotope is. So you'll be able to define the term isotope and identify those subatomic particles that are responsible for making an isotope, and understand the isotopic notation of the elements. Now you've seen this type of key here on your periodic tables, okay? And now you're going to start to see slight variations on it. For example, you see here, this is oxygen, oxygen, and oxygen, you know? You look at this number, and it's a little bit different each time. What is different about these different samples of oxygen? They're all stable, it says, but what is it that makes them different? We're going to study on that today. First of all, what is an isotope? Well, an isotope is like an element that has lost or gained some weight. It's not lost or gained electrons or protons, but it's lost or gained neutrons, okay? This is a good picture of the three isotopes of hydrogen here. The first one is protium. You can see that the atomic mass is 1 because there's only one particle in the nucleus. The second one's called deuterium. The atomic mass is 2 because there's 2 particles in the nucleus. And the third one is tritium. Atomic mass is 3 because there are 3 particles in that nucleus. I personally wouldn't call them protium, deuterium, and tritium. Those are more common names. I personally call them hydrogen 1, hydrogen 2, or hydrogen 3. That's another way to draw the isotope notation. So that's the first way to draw isotope notation. The second is really kind of simple too. 1H1, okay, 2H1, and 3H1. The same 3 isotopes, slightly different way to write them down, a slightly different notation. And the third and final notation kind of feeds off the first one, but you would write out the word hydrogen and then dash 1 to signify that it has an atomic mass of 1. The second will be hydrogen dash 2 and 3, 4, 5, 6, so on, to show that the atomic mass is different for the different isotopes. Okay? That is the different way we draw isotopes in notation. Okay? So let's get into some nitty-gritties here. Here in our notes, you got to define the isotope. It's atom of the same element with different mass numbers. Same atomic number, but a different mass number. Same number of protons, but a different number of neutrons. That's 3 definitions in one. Okay? And so, feeding off what we've been doing in class a little bit here, you can look at this chart, and we're going to figure out the protons, neutrons, and electrons in each of these 3 isotopes of carbon. Carbon 12, carbon 13, and carbon 14. Notice the 14 has to do, the 13 has to do, and the 12 has to do with the atomic mass, not the atomic number. Atomic number, in all cases, is the same number as the protons. Okay, the protons is the atomic number, and it's right there in all cases, every case. Remember that off your periodic table keys. The number of neutrons. This is the important thing for the day. And what you do is you take the mass number, subtract the atomic number from it. So 12 minus 6. I love the way that we do this notation because it's already set up as a subtraction problem for you. 13 minus 6. 14 minus 6. That's how you figure out your neutrons. Mass minus number. Atomic mass minus atomic number. 12 minus 6 is 6. 13 minus 6 is 7. 14 minus 6 is 8. Okay? Now, the next little bit, we got to remember the difference between an atom and an ion. These are all atoms of different isotopes of carbon, 12, 13, and 14. Notice that there is not any charge written in the top right corner of the boxes. There's no number up here to show you that the number of electrons has changed. Therefore, in all 3 cases, the number of electrons is equal to the number of protons because these are neutral atoms of the isotope 12, 13, and 14 carbon. Okay? A little bit more, slightly different. Instead of drawing the isotope the way that you were expecting to see notation, we've done a slight little twist. And you do need some more information. So you get your periodic table, and you rewrite it 238 with our uranium, and you put in the atomic number 92. 240 with our uranium, and atomic number 92. And now we're ready to do protons, neutrons, and electrons again. Protons should be the easiest to find because it's the same as the atomic number, and it's 92. If it wasn't 92 for both of them, then they're not isotopes. They're actually different elements. Same atomic number, different number of neutrons, or different atomic mass. Great way to do this. This is the number of neutrons. The math's already set up for you. 238 minus 92. 240 minus 92. I got to pull out my calculator and do that. I can't do it in my head. So 238 minus 92 equals 146 neutrons in uranium-238. And I'm going to guess that there's 148 neutrons. Yep, I'm right, in uranium-240. And again, these are atoms. We do not see any charges listed in the notation. Okay, so there is no ions to deal with. There's no charge up in the top right corner. It doesn't exist. So the number of protons equals the number of electrons. Okay. These next three problems you have in your book, and probably a couple more as well as your homework. That's a practice based upon those definitions. So flip back in your notes there and make sure you can answer those three problems. All right. Also, you should now be able to determine what an isotope is as its straight definition. Also, you need to understand those three different ways of drawing an isotope, like this: 1H1, 2H1, 3H1, or hydrogen 1, hydrogen 2, hydrogen 3. Okay? Or, of course, you could do the third option, which is write the word hydrogen out. So you understand there's three different ways to write an isotope on paper, and the definition of an isotope has to do with its number of subatomic particles. Thanks so much for watching, everybody. Have a good day.